Hello everyone, hope you guys are doing fine today. I have been prevented from uploading videos to YouTube for the past 2 weeks, and my channel now is hanging by a thread. But we've got to move on, and if YouTube decides to delete my channel, well, I will start all over again from scratch. I would like to give a shout out to Nathan Oakley and his show The Flat Earth Debate, which has brought up the subject of celestial navigation in the last few episodes. That will be the theme of our video today. When I first heard of equatorial horizon, in the years before I found out about flat Earth, I imagined someone standing at the equator, sideways, looking up and taking measurements from that point of the globe. Yes, I thought that taking measurements using the equatorial horizon meant to be at the equator only and nowhere else, being sideways. But then I understood what they meant by equatorial horizon and celestial equator. When they refer to equatorial horizon, they divide Earth in two halves. Get rid of the upper half and use the flattened surface of the bottom half to do all of their calculations. Let me demonstrate it here for you. Here you see on image number 1 how they laid out the parallel lines, and on image number 2 how they laid out the longitude lines. Yes, this was made using Euclidean geometry, or simply put, flat Earth math. Yes, this was made assuming Earth to be flat, and not a ball. When I demonstrated in one of my videos that the so-called Great Circle routes are nothing more and nothing less than shortcuts within these Euclidean-based parallel lines, I knew exactly what I was talking about. But let's have this conversation at another time. Using Euclidean flat Earth geometry, between 1500 and 1600, the Portuguese had already sailed the whole world. In fact, in a collection of Portuguese maps dating from the late 1500s, they even had the coast of Australia mapped out. The remote island of Tristan da Cunha had already been marked with the coordinates 37 degrees south, 12 degrees west, using Euclidean geometry. Tristan da Cunha was discovered by the Portuguese in 1506. Yes, the whole world had already been mapped out and divided using Euclidean geometry. It wasn't until the 1800s, yes, 1800s, you heard it well, that the ball earth geometry was introduced by a German mathematician. His name was George Bernhard Riemann. So why do we really need ball earth math once the whole world had already been mapped out and divided using flat earth geometry? Apparently, just to give life to a globe earth idea. Globe earth math is not used anywhere, and that's what I'm going to show you today. When using celestial navigation, they always assume Earth to be flat. They call this equatorial horizon. That funny thing they do imagining cutting Earth in half. Once you consider the part where you are to be flat, you start making your measurements. Here you see the protractor and imagine the person in the center taking angles and measurements. Don't forget to ignore the lower part. It's only for decorative purpose anyway. The Portuguese were masters at sea. They invented the astrolabe. They had already sailed the whole world by the late 1500s. With the sextant, they measured distance using triangulation, always considering the 90 degrees angle from the horizon up to the sun, moon, or a star, and that's how they navigated the world. To locate themselves on the open ocean, navigators can determine their position by observing the sun, moon, stars, and the so-called planets. Now remember this, when they talk about celestial equator or equatorial horizon, no matter how pretty of an image of a globe in space they show you. You can always cross out the lower part of this globe because it's never used. The luminaries considered to be on the bottom of this ball Earth is truly converged beyond the horizon on a flat plane. Once you approach their direction, they will rise up in the sky. They are not hidden on the bottom of the universe. Now the flat plane you always see in their celestial equator model, you can replace by a flat Earth map. There you have it. The true nature of our world. It is flat. They just don't like to admit it. They call it celestial equator or equatorial horizon. And yes, they too consider a personal dome. Professor Phoney, not Professor Dave, left at the idea of a personal dome. But this is considered in celestial navigation because this is the reality of our flat plane. We don't see it infinitely. You have to consider only the area where you can observe the sky. Here we are in a website from the University of Nebraska-Lincoln. You can ignore the celestial sphere view. Let's just focus on the Horizon Program view. You see how flat the person stands. They always consider a flat surface, which they call the equatorial horizon. You can move the stars up and down, but the surface where the person stands is always a flat plane. Now that's the personal dome. It's where as much as the person can see. And you can change the person, for example, right now, it was in North America, you can move it to Africa, to Asia, down to Australia, or South America, or back to North America. The surface will always be considered flat. You can just change the person, and wherever that person goes, you will have the celestial dome. You ignore the lower parts because the part is never accounted anyway. Let's position him in Brazil. And there you see the flat surface of the plane. You just ignore the lower part. That's how it is. Let's now go back to our flat Earth, equatorial horizon. Our measurements are made using right triangle with a 90 degrees. The baseline is always flat because Earth is flat. You cannot have a 90-degree angle with a flat baseline on a ball Earth. Nowhere have I found any calculation using ball Earth math. Real calculations. The baseline has to be flat, otherwise a 90-degree angle cannot be reached on the vertical and the horizontal lines. Let's listen to the so-called experts, say NASA, stating the very same thing.
So, how was the activity? Hopefully, it helped reinforce the math concepts you learned earlier in today's program. Now, let's review.
On a sheet of paper along the bottom, we draw a line 10 centimeters long to represent our baseline. For this exercise, let the scale be 1 meter equals 1 centimeter. Mark one end of the drawn line as point A and the other end as point B. Using our protractor at point A, we measure an angle that is the same number of degrees as the angle we measured outside for point A. Let's mark and draw the angle. At point B, we do the same thing. Now measure an angle that is the same number of degrees as the angle we measured outside for point B. As you can see, the two lines intersect. We mark the point of intersection as point C. Now we draw a line perpendicular from point C to the baseline. Using our metric ruler, we can measure the distance of this perpendicular line. Finally, using the scale 1 meter equals 1 centimeter, we can approximate the distance the actual object was from the baseline. For our case, the object is approximately 20 meters away.
Yep, there you have it. Now let's look at some math-related videos which use the same calculations. A right triangle with a flat baseline in every rate of descent calculated in the world.
Now that our diagram is complete, we can find the value of d. When you have a right triangle and you know, in addition to the right angle, the measure of one of the acute angles and the length of one of the sides, you can find all of the other pieces of the triangle. You can find the lengths of the other two legs, the measure of the additional angle. In this case, I only need to find the length of the other leg.
5,000 feet. Take a look at your instruments, and if you're at approximately this altitude, you may continue your descent with a rate that gives you a 3-degree path. This rate will depend on your ground speed, and you can find a video on this topic on my channel. This video will briefly explain how to calculate a rate of descent for a given airspeed and glide path. For example, a jet with an approach speed of 140 knots descending on a path of 3 degrees will need to descend at a rate of 743 feet per minute, but if it wants to descend on a path of 6 degrees, it will need to descend twice as fast. If you don't have a scientific calculator nearby, for a glide path of 3 degrees, multiply your approach speed by 5.31 to get the rate of descent. Alternatively, you can just multiply it by 5 to get an approximate result.
No matter the rate of descent, whether it's 3 degrees, 4 degrees, or even 6 degrees, the baseline, or ground where the calculation is being made, is always considered to be flat, because Earth is flat. Let's just take a look at one more example.
As you see on the PFD and ND, we're at 27,000 feet with a speed of 320 knots. We want to calculate the distance we need to fly a continuous descent profile. So we're going to cross out the last digits and divide that by 3. So 270 divided by 3 equals 90. So 90 nautical miles is the minimum distance we'll need for our descent.
Here we need a minimum of 90 nautical miles of flat land, or flat baseline, to calculate our descent. 90 nautical miles equals to about 103 miles. Let's now put this information on our Earth curve calculator and look at the bulge between the 2 points. You see the horizon dividing the 2 points and the position of the aircraft at 27,000 feet. Let's now apply the triangulation with the flat baseline, because this is the way it's done, and see what happens. There you have it. Why not such calculations is ever applied using ball Earth math? Because Earth is not a ball. We live on a flat, intelligently designed Earth, with the luminaries rotating above us. As the scriptures say, the heavens declare the glory of God, and the firmament shows his handiwork. And they that be wise shall shine as the brightness of the firmament, and they that turn many to righteousness as the stars forever and ever. So why are there so many government documents assuming a flat, non-rotating Earth? Because in fact Earth is flat. Check this out.
But this is a NASA technical manual. MIT, the Army Research Laboratory, flying over a flat, non-rotating Earth. Flat Earth with a flat Earth assumption. Non-rotating flat Earth. A flat, non-rotating Earth may be assumed. A flat and non-rotating, assuming a flat Earth. Flat, non-rotating Earth. A non-rotating Earth. Flat, non-rotating Earth. Validity of flat Earth based on a flat Earth assumption for a flat Earth and a flat atmosphere. Flat, non-rotating Earth. The flat Earth model. Propagation of electromagnetic fields over flat Earth. Ballistic vehicle motion. A closed-form solution is developed for the motion of a ballistic vehicle entering the atmosphere over a flat, non-rotating Earth. The assumption of these equations assume a flat Earth.
Earth is not just assumed to be flat. Earth is flat. Till next time, this is Flat Earth, Banjo, USA, Japan, and Brazil. Take care.